So welcome back to Multigrid Methods. We're in chapter 5, um, and we're talking about the basic building blocks of multigrid. And last time we introduced this hierarchy of what we called multigrid levels. We defined the canonical level inner product. We showed this, or we spoke about this coarse fine transposition property where we ratchet between subsequent levels in the mesh or in the grid. Again, I'm going to refer to things as grids, meshes, but there really aren't any grids right now or meshes because we're at a fairly abstract level. We introduced the restriction operator and the prolongation operator, these matrices, and we argued that they satisfy a sort of ratcheting property, because the prolongation is defined as the transpose of the restriction operator. We suppose that we had a family of symmetric positive definite stiffness matrices, one matrix for every multigrid level. Now we have levels going from 0 all the way up to capital L. Previously, capital L was for us, at least in the 2-grid method, just equal to capital 1, and now L can be greater than 1 strictly. So it could be like 10, for example. But we have this family of SPD stiffness matrices, which may or may not be related to each other through a Galerkin condition. And of course, if each one is a stiffness matrix or is a symmetric positive definite stiffness matrix, we can create energy inner products with each one on each level. And so we talked about that last time. We talked about the fact that we're really interested in solving one problem, and that is if I'm given a forcing vector on the finest level, so L is always the finest level, 0 is always the coarsest possible level. We're interested in solving this problem given the stiffness matrix and this forcing vector on the finest level. What is this displacement vector ULE? We said that the exact solution is going to be denoted or designated by this capital E. We define the error vector and the residual vector, and of course they always satisfy an error residual equation. ALEL equals RL. The box just means that I can put anything up above there. So I might be interested in the residual after, for example, M steps of the multigrid algorithm, or I might just be interested in the error generated at a substep. So the box can contain various superscripts. Last time we defined this multigrid algorithm, but only in the sense of naming its parts, and now we're going to get into everything in full detail. So the idea is, of course, we want to create this multigrid operator and then give various properties of it, give a description of various pieces of it. So that's what we want to do. And we did this previously for the 2-grid operator. The difference between the multigrid operator and the 2-grid operator is multigrid is going to be like a 2-grid operator that calls itself multiple times in some sort of recursive fashion. All right, so I'm going to define this thing not on the finest level or the coarsest level, but on any level, including those and in between. So let L be something between the coarsest level and the finest level. That's our fixed level L. Let GL be some given vector in level L, and UL0 be some initial vector, some given initial vector. So this is going to be the thing that we throw into the multigrid operator that we want to improve upon. So we want to put it in as 0 and come out as 3 and have it be an improved guess. This is our initial guess, an improved guess. That's the idea. So this multigrid operator is defined recursively as follows. If we're at level L equals 0, this is the coarsest of all possible levels, then we're going to do the same thing or a similar thing that we did when we looked at the 2-grid algorithm. We're simply on the coarsest level going to invert the stiffness matrix on that courses level by multiplying by A0 inverse. Now, the idea is this guy should be cheap to compute. And I said before that we don't have available to us an inverse. However, if A0 is only 2 by 2 or 3 by 3, something fairly small, then we will have available to us the inverse. And this is how we're going to think about it. So if A is, we'll say A0 might be, for example, just some small 3 by 3 or 2 by 2 matrix, something small. Let's even go 2 by 2. That way I can. All right, so just 4 elements. And so we could use even Kramer's rule to invert this thing. Not a big deal. If it's a 1 by 1, maybe A0 is 1 by 1. So it's simply going to have a single positive element in the matrix. And this is also possible for us. So if we're on the courses level, we're just going to multiply by the inverse. In this case, we could compute the inverse via Kramer's rule here. And here we just multiply by 1 over A. No big deal. Now, if L is not equal to 0, we're going to do some special stuff. This is where the special sauce is. Now, we need a smoother, and a smoother is given to us by an iterator matrix. So if you remember, there was an equivalent way of defining a general linear iterative method as follows. We take the previous guess, we multiply by an iterator matrix, or we multiply the residual by an iterator matrix and add that on to the previous guess, and then we get our updated guess for our general linear iterative scheme. So we're going to come in with this guy. If we're not on level 0, then we're going to use that as an initialization for a smoothing process or a classical or general linear iterative scheme. And we're going to do M1 steps. And so that's the number of pre-smoothing steps. This little indicator here, or this little this notation here means I'm going to go through a loop. I'm going to do 1 up to M1. Okay, so this gets updated. So start at sigma 0. So this becomes 1, 1. Then we go all the way up to M1 minus 1. This becomes 1, M1. Once we get 1, M1, that's the last iteration that we're going to do in our pre-smoothing step. We're going to give that a new name. We're going to call that UL1, UL superscript 1. So that's the pre-smoothing phase. We had a similar pre-smoothing phase when we did the 2-grid algorithm. So let's skip over this one just for a second. We had the same sort of thing in the 2-grid algorithm. We had a course grid correction, and we had a particular way of going through that course grid correction. We did that. We added that course grid correction onto the previous best guess we had. The previous best guess came out of the smoothing step, and we got this thing, which is after course grid correction. And then we entered this post-smoothing phase. Post-smoothing, we use this as our initial guess or our initialization for a smoothing iteration. Now here we're going to symmetrize our iterator by using, instead of SL as our iterator, SL transpose. And this is exactly how you do, or how you symmetrize your smoothing step. Just use the same iterator, but with a transpose here. All right, and we do M2 steps here, M2 steps, so that our last output is UL3, M2, and that we're going to set as our UL3. That's going to be the thing that exits, or that we throw back to the user on exit from the multigrid algorithm. Now, the most important part of multigrid is what's happening here in the course grid. Some of it is a lot like what happens with the 2-grid algorithm, and some of it is completely different. What's like the 2-grid algorithm is that we calculate a residual vector from the smoothed vector. Okay, so this is just a basic residual vector on level L. So this is the level L for us is our relative fine level. And the relative course level with respect to level L is going to be L minus 1. So what we're going to do is we're going to push that vector, that residual vector, down to the course grid, the relative course grid, using a restriction operator. That's what that restriction operator was created for. Now, here is where we generate the course grid correction. I'm going to skip over that step for just a second, because everything after that step is exactly like what we did in the 2-grid algorithm. We took that thing we generated from course grid correction and we pushed it up from level L minus 1, the course grid, to level L, the relative fine grid. And we added that on to UL1 to improve that UL1, hopefully. And we call that improved guess UL2. All right, now what makes multigrid special is the magic that happens in these steps that I skipped. So let's talk about that for a second. For multigrid, it's a bit like applying a recursive application of the 2-grid algorithm. So we've just generated this residual, and now if we so what we're going to think about is, suppose we have this equation to solve, UL QL minus 1 equals RL minus 1. Okay, so that's kind of the equation that you have in the back of your mind that we're going to be solving. If we could solve this exactly, then of course what we would be doing is multiplying by the inverse, and that step there is the 2-grid. That's exactly what's solved in 2-grid. So 2-grid was QL minus 1, and I should put arrows there, is equal to AL minus 1, RL minus 1. But we argued in 2-grid that this is too expensive, or maybe too expensive. And what we might want to do is apply our 2-grid algorithm to take care of this step for us. So rather than doing what we did in 2-grid, we're going to do something new, and that's the multigrid thing, right? So let's put this off to the side because 2-grid is different than what we're going to be doing. So we're not going to do 2-grid. 2-grid for us is too expensive, perhaps. The reason is we don't want to invert this matrix. I have a typo here, right? So this should be matrix inverse. So we're going to argue that this is too expensive. We want to do something cheaper. And the cheaper thing is, well, we have this iterative process or this iterative concept lying around. Let's apply that iterative process to solve this equation. So that's exactly what we're going to do. Now, what should be a good initial guess for this thing? Well, the residual, let's hope, is something small. And this is like the error on the course level. And so a good initialization for solving this problem might be to set our initial guess to be 0. And that's what we're going to do. We're going to set this initial guess for this to be the 0 vector. And then what we're going to do is we're going to call a loop. And we're going to form a loop. We're going to do an iterative process p times. And the process is just this. We're going to apply the multigrid algorithm, which is exactly this algorithm that we're in the process of defining, but we're going to define it on the level just below, okay, on L minus 1. So actually we're on level L minus 1. We're previously defining this thing on level L, so we're applying multigrid on the level just below. So we're going to apply it with this as the right-hand side. That's because we're trying to solve this problem, and that is the right-hand side. And we're applying it on level L minus 1, and we're applying it with an initial guess that we're putting here. Okay, so initially we come in with sigma equals 0, and that's that guy. So we put the initial there, and then we're going to spit something out by doing one application of multigrid, and that gives us sigma plus 1. Sigma starts out as 0, so this becomes Q11, Q11. And then we're going to throw that back in here, and we're going to do that process again. It's going to spit out Q12, and we're going to do that again. Q12 goes in there, Q13 comes out, until we reach the p-value that we specify in advance. So this p is just some positive integer. It could be 1. If it's just 1, then we're going to just do one application of multigrid. If it's 2, we're going to do two recursive applications of multigrid, and so on. Now, what comes out of that multigrid process, you can think of this as applying the 2-grid algorithm, but in some sort of recursive fashion. Let me put my phone on silent. Good. All right, so I forgot my train of thought. In any case, we set p to be some integer value. We do a certain number of recursive calls on multigrid. What comes out in the end is this object here, okay? QL minus 1, 1 comma p. And it should be what? An approximate solution to this guy. It should be a good approximation of that. That's the idea. And of course, this is what we call the true coarse grid correction. So this coarse grid correction, we're going to call the multigrid coarse grid correction. It's not going to be exactly what we want. It's going to be an iterative approximation, but that's what's going to make this multigrid method more affordable for us. It's a more affordable version of the two-grid algorithm. We already saw that 2-grid works pretty well, converges. But we want something that's cheaper. And the 2-grid algorithm, the Achilles heel of that was that it required an inversion at the coarse level. Now at the relative coarse level, we're just going to do another application of multigrid. Once we get that coarse grid correction for multigrid, we're going to use our prolongation operator to push it up to the fine grid. So remember, prolongation pushes up, restriction pushes down. Take the prolongation matrix, multiply it times that, pushes it up to the relative fine grid, that's the level L grid. And then we're going to add that onto the current best approximation for our solution, which came from smoothing, pre-smoothing. Once we have that, then we have a new best approximation, right? Our new current best approximation is UL2. And we take UL2 and we do, as we said before, we post-smooth that using some sort of symmetrized smoothing process. That's it. That's multigrid in a nutshell. And now that you've gone through the 2-grid algorithm, going through multigrid or understanding what's happening with multigrid is not such a big deal, I hope. Okay, let me check chat. Okay, nothing important. Okay, go on. All right. So the vector, as I said, QL minus 1, 1 is what we call the multigrid coarse grid approximation. It's not exactly equal to the exact coarse grid approximation, which is this object here. And to denote the exact coarse grid approximation, or the exact coarse grid correction, I should say, coarse grid correction, I'm going to put 1e in the superscript for that. Okay, so this guy here involving the inverse at level L minus 1 is the exact coarse grid correction. That's not what we're computing. We're computing something called the multigrid coarse grid correction. However, in our error analysis, this is going to be quite useful for us. Now, in the 2-grid algorithm, we found that we computed the coarse grid correction exactly. In other words, we had where L was equal to 1, we had, in our example, 2-grid example, we computed the coarse grid correction exactly. In the multigrid method, this is no longer going to be the case. We're only going to get an approximation of the exact. So much of the analysis that we're going to do with multigrid is going to revolve around finding an approximation for this difference. They're not equal anymore, so this is not zero. We have to approximate this to get an understanding of the error that we're generating with our multigrid approximation. All right, now that we have the multigrid operator defined, then defining the generic multigrid algorithm is fairly easy. So now we have a bunch of things that we need to specify. For example, M1 is the number of pre-smoothing steps, M2 is the number of post-smoothing steps, and P is what we call the cycle number. That's just some positive integer. Oftentimes, well, at least we saw this in the two-grid algorithm, we can throw away one of these smoothing steps. Oftentimes, M2 is set equal to 0 to give what's called a one-sided method. Now, we never set both M1 and M2 equal to 0 because that's going to lead to an algorithm that actually doesn't converge. A typical value of P is going to be either P equals 1 or P equals 2. So P equals 1 or P equals 2, that's a common value. Sometimes we're going to symmetrize this algorithm by making M1 and M2 exactly equal to each other. We're going to do this a lot actually in this chapter. All right, but in any case, those need to be specified. Now, the multigrid algorithm, then once these guys are specified, then it's fully defined, it's completely defined, and here it is. So suppose that you're given, now for example, or K is no longer going to be our wave number because we're not talking about Fourier stuff anymore. So K is going to be the iteration number. Suppose we have ULK, capital L is our finest level, and we want to improve upon that using our multigrid algorithm. Remember what we're trying to solve. We want to solve this equation here. So we're given this, and we're given an initialization, and we want to improve upon it. And we're going to use the multigrid algorithm to do that, and it's defined precisely as ULK plus 1 is equal to multigrid operator that we just defined with the following inputs: FL, capital L, because we're calling it on the finest possible level, and we're using as our first input, or our input, ULK, and we're going to improve upon that and call that improvement ULK plus 1. And that's it. That's the multigrid algorithm completely defined. Now, let me give some nomenclature that's common in multigrid. So a multigrid algorithm is called one-sided, as we said before, just like the two-grid method, if M2 is equal to 0 and M1 is greater than or equal to 1. The algorithm is called a W cycle if P is greater than or equal to 2, and oftentimes we're just going to call a W cycle whenever P is equal to 2. It's called a V cycle whenever P is equal to 1, and I'm going to show you why that's called that in a second. The algorithm is called symmetrized or completely symmetric if M1 equals M2. And we say that the algorithm is a simple symmetric V cycle if P is equal to 1 and M1 and M2 are both equal to 1. It turns out that this method actually is going to converge for us. We could prove this. Now, why is it called a W cycle whenever P is equal to 2 and a V cycle whenever P is equal to 1? That has to do with the structure of the calling. So whenever W is equal to 2, or sorry, P is equal to 2, we call this a W algorithm or W cycle, and P equals 1, we call it a V cycle. Suppose that capital L is equal to 2. So that's our finest possible level. Our coarsest possible level is L equals 0. And so whenever P is equal to 2, let's think about what we do. So our first step is we do a smoothing in our algorithm. So that is this part right here, free smoothing. And then we're going to do a coarse grid correction, but we're going to do a loop of our coarse grid correction, okay? Now, if P is equal to 2, then how many times do we go through that loop? We go through once and come back up, and we go through again, and we're done at level L1. We called that twice. Go down once, go down again, and that is P equals 2, called from level L equals 1. In fact, we can go all the way back up to our finest level after exiting that loop. And remember, we called this with P equals 2, so we've got to apply a second a second loop, or second part of the loop. This is P equals 1 over here, and then P equals 2 is this part. So we go down to level 1. We're going to call that with P equals 2. So we go down once, back up again, down again, for P equals 1, P equals 2, and then all the way back up to complete our loop. So this is what a W cycle looks like if we track how we go up and down in levels. If you look at the V cycle, it only uses P equals 1 maximum, and so it goes down to the coarse level, and then just goes down to the coarse level. It keeps going down until it hits the coarsest possible level, and then finally it's going to come back up. So if you keep track of your level numbers as you're going along and do P equals 2, you're going to see that you get these sort of W shapes carved out. If I do P equals 1, then this is just going to produce something which looks like a V, keeping track of the level numbers. So this is a little exercise for you guys to go through this algorithm and convince you that that's, as I'm calling this guy, that's what's actually happening. Okay, that's what's traced out with the level numbers for P equals 2, and this is what's traced out for P equals 1. Now, if you do P equals 3, then it's a much more complicated shape, and I won't show what that looks like. Well, I guess we could try kind of take a little stab at it. It's going to do down 1, okay, and then it's going to go and then up. So this is P equals 1, P equals 2, P equals 3 for the level L equals 1. But now we've only executed P equals 1 on the finest level, so we've got to do another one down. And you can see it's a more complicated W shape. Okay, so that's P equals 1, P equals 2 on the finest level, and we've got to execute one more of these guys to complete. So I need some more room here. All right. So the last one's going to be and this is only whenever our level number, our capital L is equal to 2. It gets much more complicated as L gets larger, as you might imagine. All right, so this is overall what we mean by P equals 3. In the case that L is equal to 0, we just do a direct solve. That's all our multigrid algorithm gives us. If the Can you hear me? Give me a thumbs up if you can.
I can hear you now.
Okay. Yeah. All right. So it sounds like I'm not going to be able to use the wireless feature on these headphones. Okay. Now, as I was saying before my headphones died, in the case that L is equal to 0, all our multigrid algorithm is just a direct solve. Whenever L is equal to 1, we recover the 2-grid algorithm. That's it. So, and of course, when L is greater than 1, like 2, then we're doing something completely new. This is new territory. But it's an exercise for you to show that whenever L equals 1, we just recover the two-grid algorithm. Multigrid and 2-grid are the same whenever capital L is equal to 1. All right, now we want to find, if possible, what is the error transfer matrix for the general multigrid algorithm. And this is kind of a complicated process. And the way I'm going to do it is I'm going to define what the answer is first. I'm going to give a complete recursive definition of what the answer is, and then we're going to prove that this is the answer. This is the algorithm, or this is the matrix. Now, let me first of all say what would I mean by the error transfer matrix for multigrid? So suppose I want to solve on some generic level L, little l, ALUL E equals GL. Then how would I express the error of solving this, or the error generated by, instead of solving this, doing one application of the multigrid level on level L? So that means computing something like this, okay, with an initial guess. So no matter what I put in here, that's my initial guess. So what I'm really after is the exact solution on this level minus the multigrid approximation generated by computing UL0. All right, and that we can show is exactly equal to EL, some matrix, which I'm going to define momentarily, times that error. So the error is the exact solution minus whatever I put in there as my initializer, my initial guess. So whatever this guy is should be the error transfer matrix for the multigrid algorithm, but only at this level, this one level. This error transfer matrix is going to be a recursively defined object. And so let's get into the recursive definition of it. It's kind of complicated. Now, on level L equals 0, we're not going to have any error because we're going to, in our multigrid algorithm, we solve the problem exactly the same way we did with the 2-grid algorithm. So we can define our matrix, our error on level 0, L equals 0, as just the 0 matrix. All right, now it's the 0 matrix with n0 rows and n0 columns, that 0 matrix. Okay, so if n0 is equal to 2, so for example, if n0 is equal to 2, then this is the 0 matrix that has 2 rows and 2 columns of zeros. And now I'm not specifying what n0 is. It might be 2, it might be 1, it might be anything. We're just going to be generic about it at this moment. But that's what I'm defining right now as the error matrix on level 0. All right, now for any level which is L equals 1 or greater, then here's how I'm going to make this definition. EL is equal to the error transfer matrix for post-smoothing. Okay, so that's the smoothing that I do after I exit the multigrid recursive call. Okay, times a bunch of stuff, which I'm going to define momentarily, times the error transfer matrix for pre-smoothing. This is pretty clearly the error transfer matrix for pre-smoothing. All right, and remember what its definition is. It's just going to be KL is equal to I minus SL. This is IL SL times AL. Okay, the error transfer matrix for pre-smoothing, and then post-smoothing is going to be that comes with a star. Now yeah, that's defined here. Okay. Error transfer matrix, I guess I should have looked, but those are the error transfer transfer matrices for the smoothing process. And if I would have just looked ahead, I would have seen that they're defined. Now, the hard stuff is everything that's defined in here. Okay, that's kind of the new stuff as well. All right, so this is the stuff in the middle is IL minus the prolongation matrix PL minus 1. Remember, this pushes stuff from the coarse level L minus 1 up to the fine level L times IL minus 1 minus EL minus 1 raised to the P power. Okay, we'll get into what this is. And then finally times pi L minus 1. Now, pi L minus 1 is the same, it has the same definition as we had when we were talking about the two-grid method. Pi L minus 1 is AL minus 1 inverse times the restriction matrix times the fine grid stiffness matrix. So the inverse of the stiffness matrix on the coarse level times the restriction matrix times the fine level stiffness matrix again. Now it makes it's useful for you to make sure that this makes sense as multiplication and figure out what are the sizes of these objects. Well, this is L minus 1 by L minus 1. This is L by L. And this guy here, what is the size of that? Well, the restriction matrix takes things from the fine level and pushes them down to the coarse level. So this guy is going to be L minus 1 by L. So this makes sense for multiplication. It's compatible for multiplication. And it's a matrix with L minus 1 rows and L columns. Now, that's not the same as the thing we called the coarse grid rich projection. That was slightly different. Remember, the coarse grid rich projection was PL minus 1 times pi L minus 1, and we gave that a tilde. It's defined here in multigrid setting the same as it was defined, or similarly to how it was defined in the two-grid setting. Only in the two-grid setting, this was a 1, and L minus 1 was therefore a 0, etc. So the new thing for us, the really new thing here is in the two-grid, we didn't have this piece. So what is that new piece? So think about what two-grid looked like. If you can remember the error transfer matrix. It's probably impossible for you to do that, but it was in the middle here, just I minus pi L tilde. IL minus pi L tilde. Well, we would get that if this thing was not there. If that thing was just equal to 0, then we would just get the error transfer matrix for the two-grid algorithm. Well, let's look at this whenever L is equal to, little l is equal to 1. In fact, we do recover exactly the error transfer matrix for the two-grid algorithm, because whenever L is equal to 1, L minus 1, okay, the error transfer matrix for L minus 1, that's L minus 1 is equal to 0, is just going to be the 0 matrix. So identity minus the 0 matrix is just the identity. So this part here goes away, and we just get pi L tilde. So the new thing here for us is this object here. And this comes because instead of solving the coarse grid problem exactly, we're going to apply multigrid to solve that coarse grid problem. And we're going to do a recursive application. And so this is the new thing. Just to point out something that we covered in chapter 2, I might have said chapter 3 when I was referring to the basic bare bones of the two-grid algorithm. It's chapter 2, where we showed that we showed a computation like this. We showed that if I have KL appearing on this side of the energy inner product, and I move it over to the other side, that's what we call the adjoint with respect to the energy norm, or the energy inner product. Well, it moves over with a star. That star is precisely this guy here. Okay, so this is what we call a self-adjoint smoothing process, self-adjoint smoothing process.
or sometimes just symmetrized smoothing. The fact that this is equal to itself, okay? Or, well, sorry. This is not necessarily equal to KL star, but the KL star is equal to that. So it's symmetrized if we have KL star here and KL here. It's going to be completely symmetrized if M1 and M2 are exactly equal to each other, and that's what we're going to assume momentarily. All right, so now I want to actually prove that this complicated, and by the way, it's recursively defined because this error transfer matrix is defined by the error transfer matrix on the level below. So we want to prove that this is actually the error transfer matrix that we get by doing one application of the multigrid generic algorithm on level L, some generic level L. Now, if we can prove this, that error transfer matrix really is the generic on level L, then the one that we really need to analyze is going to be this error transfer matrix, E capital L, because what we're really interested in is the error on level capital L. Right? So the proof is by induction, and there are two cases which actually should be clear. We're going to use induction on L, and the first one is if L is equal to 1, then our algorithm is just an inversion of the stiffness matrix. There is no error at all. So we define the error to be 0, and therefore we're clearly correct. Because there is no error, there's no error transfer, because you do an exact inversion on level L. There's no error, so EL where L is equal to 0, should just be the 0 matrix. We also know that we're correct for the two grid case where little l is equal to 1. We showed that when we defined what the error matrix was, that recursively defined object. And that's because the error on level L equals 0 was exactly equal to 0. So the induction hypothesis is going to be, let's assume that it's going to be true on some generic level L minus 1 and show that we get that error, the generically defined thing on level L. So we're going to assume the result is true on level L minus 1. In other words, we're going to assume that if we are given an exact solution of this problem on level L minus 1, then the error generated by doing one application of multigrid using this as an initialization, one application of multigrid using that as initialization, then our error is transferred via this transfer matrix EL minus 1. That's the induction hypothesis. This is the true error that we want to compute. And what we're saying is it's exactly equal to the error at the previous stage, or for whatever the error was with this initial guess, times a matrix, and that matrix is EL minus 1 just defined. So this is our induction hypothesis, and we want to show that the recursively defined version of the error holds true at the next level up. Just knowing that information. All right, so that means that we've got to assume that we're applying this at level L. Okay, generic level L. But before we do that, let's define a few more pieces. Suppose that QL minus 1, 1E, RL minus 1, 1 satisfy the following relation. Remember, this conforms to what we talked about earlier in the definition of our multigrid operator. This object here is what we call the exact coarse grid correction. The exact coarse grid correction, given that we have something like this, which is the residual. Now, this is actually the residual on L minus 1, the actual residual that I'll define momentarily. Now, using the induction hypothesis, if we're trying to solve this problem here, then the induction hypothesis tells us if we put in an initial guess of 0, trying to solve this problem here, initial guess of 0 for this true course grid correction, right? Then what we should get is the error EL minus 1 times the true solution minus the initial, but this is just this exact course grid correction because our initial guess was 0. So that's given to us by the induction hypothesis. Now, let's write this in terms of the definitions that we introduced in the or the terminology that or notation we use in defining the multigrid operator. QL minus 1, 1E, that's the exact thing that we're after in this solution here. If we do one application of multigrid, then what pops out is this guy. And so what we should, and that's with 0 as our error. So one application of multigrid with this as our initial guess is just equal to EL minus 1, QL minus 1, 1E. Okay. Now, if we apply that again by using now the thing we just computed as the input for our multigrid operator again. So this is because we're doing that loop right in the center. We're doing that P times. Then we get EL minus 1 squared, QL minus 1, 1E. When we try to compute the error between the exact course grid correction and the next object that we obtain by applying our multigrid algorithm. If you keep doing this, then you're going to get this raised to the P power, and P is going to go in this position. So if we continue in this fashion, then we have the true course grid correction minus the approximated course grid correction from our multigrid algorithm is equal to EL minus 1 to the P power times the true course grid correction. All right, so now what comes out of our multigrid algorithm is, or what we put into the multigrid algorithm initially, remember, is the thing that goes in there to start. The initialization for our multigrid algorithm is, oh, no, sorry. This guy here, I made a mistake. This guy here just gets defined as this object. That's from our definition of multigrid. That's just by definition, okay? Once we finish our multigrid application of the P cycle, then we come out and we define this object. That is the course grid correction that we're actually going to use in our multigrid. So it comes out labeled like that. We're going to relabel it like that. Okay, now let's see. Is that true? Let me think about that for a second. I thought we called this guy. I want to go back and yeah, no, that is right. That is right. Let's go back. Let's go back and make sure that we set this guy equal to that. Yep, there it is right there. That guy was just set equal to that. I was thinking it should get a 2, and I was confusing myself for just a second there. But it's not a 2. We don't call it a 2 until we actually push that thing up to the fine grid and then add it on to the previous best guess. So I was thinking this should be a 2, but no, it's 1. So this is just a relabeling. Okay, now let's solve for this guy. Let's solve for this guy, and we'll get something which appears in the definition of our generic error. So if we solve for this, move that guy over, and you just realize that this appears twice, right? We can use the distributive property to pull that common vector out, and we get QL minus 1, 1 is equal to the identity minus the error to the P power at level L minus 1 quantity times the true course grid correction. So this is actually the error. This tells us this part here is the error that we generate by not solving that problem exactly on the course level. All right. So the error of our course grid correction. That's the error of our course grid correction. And this, therefore, is the error transfer matrix of the course grid correction part. So now I think you probably believe that this is what appears in the error. This is the new thing. So let's see how it gets there. All right, so now let's go back. QL minus 1, 1E. How was that defined? This is the exact course grid correction. Well, it's the inverse of the L minus 1 stiffness matrix applied to RL minus 1, 1. This guy, let's eliminate that. That is just equal to GL minus ALUL1. Okay, so that's a residual, and there's the definition of that residual. Now why do we get this matrix? And the reason we get this matrix is, remember, this guy was defined by restricting this guy to the course grid, the relative course grid. So this is by definition. If you go back to, let's just go back for a second. Right, so there is our residual, and we project it or push it down to the course grid through this action here, and this is the object we're defining. So it's restriction matrix times that residual. Okay, so restriction matrix times that residual on the fine grid. Next, well, this is a residual equation. Remember, we have what's called as the error residual relation, or the error residual equation. So anytime we have a residual, just think there's some error associated to that through the error residual equation. This then is here. This is a residual, and therefore this is A times the error through that error residual equation. What is the error? It's ULE minus UL1. That's the error at level, the generic level L. This thing here was what we called the pi L1 matrix, with not the pi L1 tilde. It's not a square matrix. It's a non-square matrix called the pi L minus 1 matrix. This is what we defined whenever we were defining the error matrix in general, that recursively defined error matrix. This is, again, just the error brought down from the previous equation. So this is equation 5. Let's put that in our back pocket. Okay, so now this is what we've done is define this so we can put that in here. Okay, so if I multiply this times that just gives me the QL minus 1, 1 vector. So there's the error vector, or the error matrix for our course grid correction. This is the error we make by not solving the course grid correction exactly. And we have this pi L minus 1 times our error. Now, for the error after post-smoothing, that is just the exact minus the smooth solution. That one is just given to us by the error for the post-smoothing step. That's the error matrix for that process. Raise to the m2 power because we're doing it m2 times. The exact solution minus the previous solution, the previous best guess solution. That's the solution that we get out of the course grid correction step. For the error after the course grid correction step, what is that? That is just going to be ultimately equal to so it's this true solution minus this guy here is defined as the previous best guess that we had after pre-smoothing plus the course grid correction. Okay, so this is the prolongation applied to the course grid correction that we just computed here. So now we're going to take that guy and dump it into there. And then we're going to do a little bit of algebra. We're going to see that we have the error appearing twice. We're going to use the distributive property to pull that error out. And there we go. So now we have a description of the error that we get after the course grid correction step. It's this new matrix here, and this is that new ugly piece that is brand new. Remember, I said if this wasn't here, this would just be exactly like we had in the two-grid algorithm. The error after pre-smoothing, of course, is just the pre-smoothing error matrix, error transfer matrix, KL. We raise to the M1 power because we're doing M1 smoothing steps, times the error that we have just between the true solution and the initial vector that we throw into the multigrid algorithm. So now we can just put everything together. This vector is matrix times vector. We can put that in there. And this guy we can put in there. And finally, and that's it. That gives us exactly the definition that we wanted, right? So it's this times that in that order. Okay. Let's see. Or maybe I should say it as you have to reverse the orders. It's this times that times that. So just go back a couple of slides and you'll see it. It's that times the new ugly beast that we just computed times the smoothing error. So post smoothing, course grid correction error, pre-smoothing. Post smoothing error, course grid correction error, pre-smoothing. Okay, so we just proved the result. So it holds by induction that this is our error transfer in computing or applying one application of multigrid using this as an initial guess. One application of multigrid generates a new error, and that is equal to the previous error times this matrix. So that must be the error transfer matrix by doing a step of multigrid. And that's it. That's the long and the long and the long of it, I guess. All right, so the next section talks about a generalization of what we mean by the Galerkin condition and what are the implications of assuming this Galerkin condition. So this is similar to what we discussed in chapter 2 when we were talking about the Galerkin condition in the generic two-grid algorithm. Now we have a full family of stiffness matrices, so we need to figure out how that condition generalizes. So we say that the stiffness matrices satisfy the strong Galerkin condition, assumption A0, if and only if they all satisfy, the whole family satisfies this wrap condition structure. AL minus 1 is equal to RL minus 1, AL, PL minus 1. For all L between 1 and capital L. So previously, when we defined the Galerkin condition, we didn't add this word strong Galerkin condition. What was it? It was just that A0 was R0, A1, P0. That was all we had. Now we have a full family of stiffness matrices. We're going to assume that they all satisfy these types of conditions. That's the easiest way to generalize that strong Galerkin condition or that Galerkin condition that we need. It's the easiest way to generalize it, and we're going to give it the added adjective strong because there's another way to generalize this. Now, in multigrid, we're going to be become acquainted with our first generic assumption or our first numbered assumption, A0. So we say that the strong Galerkin condition is equivalently called the assumption A0. Some people love these assumptions. Some people hate them. They're easy to hate because assumption A0 is a lot less instructive and self-explanatory than the strong Galerkin condition. Strong Galerkin condition or the wrap condition, the words make more sense. But in multigrid, there's this tradition of naming assumptions just with numbers. And we're going to follow that to some extent. Um, we're not going to follow it completely. So the reason why I say we're not going to follow it completely is number one, because of the thing I just mentioned, these are not really explanatory. They don't say what they actually mean. You have to remember these guys in a sort of vacuum. But these this is, as I said, it's traditional in the multigrid literature to give these simple numbers. So we're going to connect them in that way. So the thing I want to mention though is whenever I mention or state the assumption A0, I mean that's nice because we can just call it assumption A0 and use the label A0. But I'm oftentimes going to mention alongside of assumption A0 the strong Galerkin condition. So I'll just be repetitive about it. Strong Galerkin condition means assumption A0. Assumption A0 means strong Galerkin condition. So we'll just keep those hand in hand. Now, there is also something called the weak Galerkin condition, and we call that assumption A1. That holds if and only if for all VL in RNL, and I might just say all VL in level L to make life simple on us, all VL in level L. VL in the energy inner product is greater than or equal to the pi L minus 1 projection times VL against itself in the AL minus 1 energy norm. So this is the energy norm on the level just below. And if this condition holds, then that's what we're going to call the weak Galerkin condition, if it holds for any arbitrary vector VL. So let's see, this has to be one index larger than that. So this guy can go all the way down to 0 total index. So that means L has to be bounded below by 1 for things to make sense. So L minus 1 is going to be 0. But it can go all the way up to L equals capital L. Okay, so everything makes sense. Well, I suppose that if we call something the strong Galerkin condition and something else is called the weak Galerkin condition, that the strong should imply the weak Galerkin condition. And this is exactly what happens. So we're going to show that A0 implies A1. If assumption A0 holds, so to do this, we need to prove something before that, though. And the thing that we need is that if the strong Galerkin condition holds, then the pi L tilde matrix is a bona fide projection matrix. Okay, so this is what we previously called the Ritz projection matrix. And we gave it the name projection matrix because it was a projection as long as the Galerkin condition holds. Well, if A0 holds, strong Galerkin condition, then this holds. And actually the proof is quite a bit similar to what we had previously in chapter 2. All right, now it also turns out that pi L star, that's the adjoint in the L energy inner product is just equal to pi L tilde. So this is self-adjoint even if assumption A0 does not hold. Okay, so it's always going to be, just by its definition, self-adjoint. All right, so let's prove this. If the Galerkin condition should say strong Galerkin condition, if the strong Galerkin condition holds, what does that mean? That means AL minus 1 is RL, AL, PL minus 1. The wrap condition holds. And we recall the definition of pi L tilde. It's PL minus 1, AL minus 1 inverse, RL minus 1, AL. That's the definition if you go back a few slides. And now all we have to do is plug in our definitions. Okay, so if we do that, we're trying to show that this is really a projection matrix. So let's multiply it times itself. So there's that first one, and there's the second one, multiplied times itself. Now all we need to do is a regrouping. we get RL minus 1, AL, PL minus 1. If the Galerkin condition holds, then that's the AL minus 1 matrix. That's the AL minus 1 stiffness matrix. And that can cancel with either its neighbor on the right or the neighbor on the left. One of those two can be canceled. And what we're left with is PL minus 1 AL minus 1 inverse, RL minus 1 AL. That's just the pi L tilde matrix back. Okay, so there is, if the strong Galerkin condition holds, then we clearly have that pi L tilde matrix is a bona fide projection matrix. All right, so now we want to show that no matter what, pi L tilde is always self-adjoint with respect to the energy inner product. So this just requires writing out the definitions. Okay, so um, a lot of the proofs that we do in this class really do come down to just figuring out what the heck this says. Well, if we want to show that this is self-adjoint in the A, or self-adjoint with respect to AL inner product, we need to show that when we move this to the other side, then we just pick up that star. Okay, and then if we pick up, well, we know that by definition. If we just move it to the other side, we get the thing back itself. That's what I actually want to say. So what we're going to do is use the definition of this with respect to the L inner product, the level L inner product. So that just means you multiply this times whatever was over here, AL, pi L tilde UL VL. UL and VL are arbitrary. Now we're going to use the definition of the pi L tilde matrix. That's all of that stuff right there. All right. Now what do we do? Let's do a regrouping. Let's use the associative property and group this bit together. Okay, so that's that bit there. And now let's throw that to the other side. But now since we're in the inner product, the level L Euclidean inner product, that goes to the other side with a transpose of the product. Okay, or yeah, the transpose of the product. Well, how do we do a transpose of the product? You multiply you take the product in reverse order and take transposes. What we're left with on this side is just ALU. When we threw this guy to the other side, it becomes the transpose of all that. So that means we do RL minus 1 transpose. That's PL. This is self-adjoint, okay? Because remember, we assumed that it's a family of self-adjoint operators. This becomes RL minus 1, and this guy is also self-adjoint. So what we get then back is just the pi L tilde matrix. Well, that guy, we're still in the L inner product, so let's bring that guy out. Finally, we get this. So this shows that when we move this guy to the other side, it remained the same, and therefore, generically, this has to be the adjoint operator, or the adjoint matrix. So this is pi L tilde star, but we showed that this comes over and it remains itself, so this is our self-adjoint statement. So no matter what we choose for our family of stiffness matrices, whether they solve the strong Galerkin condition or not, they're always going to be self-adjoint. As a corollary, we have that the matrix IL minus pi L tilde is also going to be self-adjoint. That's just because we're adding something which is self-adjoint onto it. So this matrix is also self-adjoint, no matter what, no matter what. But if assumption A0 holds, this is the strong Galerkin condition holds, then this matrix is also a projection matrix. Remember, that's easy to show. If we know that we have a projection matrix, then I minus that projection matrix is also a projection matrix. That's a little theorem that you learn from numerical analysis or advanced linear algebra. All right, so that that's a little that's something that follows from assuming that the strong Galerkin condition holds. Now we're in a position to show that the strong Galerkin condition implies the weak Galerkin condition. A0 implies assumption A1. Strong Galerkin condition, weak Galerkin condition. All right, so remember what the weak Galerkin condition was. We want to show that this guy is greater than or equal to, no, let's see, I need to go back and remind myself because So we want to show that this is greater than or equal to this object here. Okay. This object measured in this energy inner product is greater than this object measured in this energy inner product. All right. So that's what we want to show. So let's take this object and let's just figure out what's going on with that. What is this object going to be? Well, it's measured in the AL-1 energy inner product. Let's bring that guy out and attach it to one of these sides. Doesn't matter which side we attach it to because it's a symmetric matrix with respect to the L-1 inner product. So I can attach it here, but then I can immediately move it over to here. All right. So we do that. Then let's use the definition of this this operator. Remember, that's just AL-1 inverse RL-1 AL, but it's multiplied now by this guy, AL-1. They annihilate each other. And what I'm left with is pi L-1 VL, RL-1 AL VL. All right, so let's move this guy to the other side. This moves to the other side using our little ratchet identity. So it goes over to the other side. I can immediately give that the name PL-1, or I can remind myself that this is going to be the transpose at first. But notice that the space ratchets, or the inner product from the space ratchets from L-1 up to L. All right, so this is PL-1, pi L-1. PL-1 times pi L-1, that's the pi L tilde inner product. I can move this guy out of there, out of this canonical inner product and create an energy inner product. And so clearly, if this guy is pi L tilde, what I get in the end is pi L tilde VL, VL, AL. Right? So that's the first step I need. So the last calculation that I need to show is that this guy minus that guy is greater than or equal to 0. And if I can show that, then if I move this guy to the other side, then I've proven exactly what I wanted to show. We're going to use that last calculation, namely that this is equal to that, to obtain exactly that. So we want to show that this is greater than or equal to 0. That will give us what we want. That's the weak Galerkin condition. So how do we show that? So let's just use the definition. This guy we're going to leave the same. This guy here, how can we replace this with that? Well, that's the inequality that we just showed. That's the inequality that we just showed. All right. So now I can use the linearity of this inner product. This is an inner product just the same as any other inner product. It has the linearity property, so I can combine these two things together. This guy being the same to get this. Okay, using my inner product. Linearity, the first component. Now I'm going to use the fact that this guy is a projection matrix. It's equal to its own square. I can move one of those guys over to the other side. Okay, one of those square. It moves over in this guy and this inner product with an adjoint. But remember, we showed that it's self-adjoint. No problem there. And of course, so I don't have to put the star there. I can just leave it unstarred because it's self-adjoint. And this just becomes what? This is a inner product in the energy inner product specifically of a vector with itself. So this is a norm squared. Norm squared. And this has to be greater than or equal to 0 because it's a norm. It's a norm squared. So it's obviously greater than or equal to 0. I can move this guy to the other side, and that's precisely the weak Galerkin condition, assumption A1. So we just proved that assumption A0 implies assumption A1. A strong Galerkin condition implies the weak Galerkin condition. We're going to pick up from there next time. We'll talk about more assumptions. Yay, more numbered assumptions. This one, assumption A2, doesn't really have a name. And so we don't have any good name to attach to it. Maybe we can think about one. But I'm going to stop there and I'll take any questions that you guys might have.